Have you ever wondered how an AI can look at nothing but pure random noise and suddenly create a photorealistic face of a person who doesn't even exist? Or how it can paint landscapes, generate music, design products, or even mimic an artist's style with such uncanny precision that you'd swear it was magic? Well, today you're about to discover the origin story of one of the most revolutionary ideas in all of modern artificial intelligence, a deceptively simple concept that changed everything. Welcome to the incredible world of Generative Adversarial Networks, or GANs, an idea so bold and powerful that it reshaped how machines create. And the best part? It all began with a single insight. What if, instead of training one neural network, you trained two and made them battle each other? But before we unlock the story behind this genius approach, make sure you smash that like button, subscribe to the channel, and hit that notification bell so you don't miss any deep dive videos just like this one. Now, let's dive into the groundbreaking paper that sparked the entire GAN revolution. At the heart of the original Generative Adversarial Nets paper lies a simple but brilliant idea. Pit two neural networks against each other in a kind of creative competition. One network, called the generator, tries to create fake data, whether that's images, audio, or anything else, while the other network, the discriminator, tries to distinguish real data from the generator's fakes. Think of it like a master counterfeiter and a highly trained detective. The generator is constantly trying to forge better and better samples, while the discriminator becomes ever more skilled at spotting forgeries. This competitive pressure forces both networks to improve in tandem. In fact, the paper describes it as a minimax two-player game. One side tries to maximize its score, while the other tries to minimize it. Early in training, the generator is terrible. It produces noisy, meaningless outputs. The discriminator easily catches these fakes and confidently labels them as counterfeit. But each time the generator receives that feedback, it learns how to adjust its parameters so that its next attempt looks just a tiny bit closer to the real thing. Over many rounds, this rivalry pushes the generator to produce samples so convincing that even the discriminator can't tell the difference. And that's the equilibrium point the theory promises. If both networks have infinite capacity and training goes perfectly, the generator will replicate the true data distribution. That means it doesn't just memorize the data, it learns the underlying patterns that define the data. The paper uses a detailed mathematical framework to show that, under ideal conditions, the generator converges to producing perfect samples, so realistic that the discriminator is forced to output 50-50 probabilities, totally unsure whether it's being shown something real or generated. The images in the paper illustrate this beautifully. Early on, the green generator curve looks nothing like the dotted curve representing real data, but as training progresses, the two curves slowly merge until they are indistinguishable. What makes this method so powerful isn't just the conceptual elegance, it's how efficiently it can be trained. Unlike older generative models that relied on Markov chains or approximations, GANs can be trained using nothing more than backpropagation, the same method used to train most modern neural networks. No sampling loops, no intractable likelihood calculations, no heavy probabilistic machinery. And that simplicity unlocked results that shocked the machine learning world. The experiments showcased in the original paper include handwritten digits from MNIST, faces from the Toronto Face dataset, and even CFAR-10 natural images. The samples, displayed without cherry-picking, show that the generator produced authentic-looking digits and faces that were not memorized from the training set. The authors even confirmed this by showing nearest neighbor comparisons, real faces next to generated ones, demonstrating that the model was genuinely learning a distribution, not copying. One of the most fascinating insights comes from the latent space, the space of random input vectors fed into the generator. When the researchers interpolated between 2 points in this latent space, the resulting outputs gradually morphed from one digit into another in smooth, natural transitions. This suggested that the generator didn't just learn to spit out images, it learned a meaningful internal representation of the underlying data structure. But GANs weren't perfect, and the paper openly discusses their challenges. One major issue is keeping the generator and discriminator in balance. If the discriminator becomes too strong too quickly, it rejects all generated samples with complete confidence, giving the generator almost no useful gradient to learn from. If the generator gets too good, the discriminator can't keep up and learning collapses. The paper famously refers to mode collapse, where the generator maps many input values to the same output, as the Helvetica scenario, because everything starts looking the same. Despite these challenges, the advantages were staggering. No Markov chains, no complicated inference, and the ability to generate extremely sharp, high-quality samples. The authors highlight that GANs can even represent degenerate or highly peaked distributions, something traditional probabilistic models struggle with. And while the original paper focused on the simplest form of GANs, it also laid out a roadmap for extensions that would soon explode into dozens of new architectures. Conditional GANs for labeled data, inference models that predict latent variables from real examples, semi-supervised learning where the discriminator's representations boost classification accuracy, and even more efficient training strategies. All of these ideas emerged directly from the foundational framework introduced in this first paper. The results and diagrams, especially the step-by-step training visuals on page 4, help the world understand how this process evolves: discriminator improving, generator adjusting, distributions aligning, and finally, equilibrium when the generator is indistinguishable from the real data. And just think about what has happened since. GANs have powered hyper-realistic image generation, deepfakes, art generation tools, video synthesis, 3D modeling, medical imaging enhancements, and so much more. But every single one of those innovations traces back to this original insight. Train two neural networks in opposition, let them battle, and watch creativity emerge from competition. As we wrap up this deep dive, take a moment to appreciate just how revolutionary this paper was. It didn't just improve generative models, it introduced an entirely new way of thinking about learning, one that fused game theory, optimization, and neural networks into a single elegant framework. And with that, thank you for watching this exploration of one of the most influential ideas in AI history. If you enjoyed this breakdown and want more long-form deep dives into legendary research papers, make sure to like the video, subscribe to the channel, and leave a comment telling us which paper you want covered next. Your engagement helps this channel grow and lets us bring you even more ambitious videos. Thanks for watching, and I'll see you in the next one.